So we're going to take a look here at 3.3 and logarithms. This is a fairly new topic. I mean, you guys should have touched base with this in Algebra 2 a little bit, but we're going to spend today, it's going to be a very basic introduction to logarithms and some of the properties. Some of the problems, are pretty simple to do. So I want to first just take a look at this graph. If we look at a graph of an exponential, right, we have all the characteristics that we've talked about last week. The graph of an exponential, as we go to the right, it goes up. It has a horizontal asymptote. Again, it goes really large, really fast. Well, a logarithm graph is the inverse of that. So it's going to look something like this, and this has a vertical asymptote. Okay. Um, as we go further and further to the right, it kind of approaches a certain value. So just understand that logarithms and exponents are inverses of one another. So I always have this conversation with my dad because he always talks about how he used to be really good at math. He said until he got to logarithms, all logarithms are exponentials. Anytime that I have something that's y equals log base b of x, I always have students say, oh, I don't know what the heck I'm supposed to do. I say, okay, write it as an exponent. So in order for you to write it as an exponent, you need to know this fact right here. If you have y equals log base b of x, okay, it will turn into, notice how I said that, log base b. Whatever this number is right here is my base. When a logarithm is written, the number on the other side of the equal side is my exponent. And then the number that's written next to my base in the logarithm is my answer of the exponent. So if I were to write these logarithms out as exponents, this would say 2 to some number is equal to 8. Now, clearly there's no x here. This isn't an equation. We're just evaluating. This is simply another way for me to write the number 3. This is the answer to that problem. It's 3. I'm evaluating. This says 3 to some power equals square root of 3. Well, how do I turn an exponent into a square root? That would be the 1/2 power. Okay. And then this one says 5 to some power equals 1 over 25. How do I go from a whole number to a fraction? It must be a negative exponent, right? And that negative is a -2 because that would be 5 to the -2nd, which equals 1 over 5 squared, which is 1 over 25. So I always say this when we're looking at logarithms and exponents. If I go from a larger number to a smaller number, that's going to be a whole number exponent, right? If my number gets larger, my answer gets larger. It's going to be a whole number exponent. If my answer goes from a whole number base to a radical, it's going to be a fractional exponent. And then if I go from a whole number to a fraction, it's going to be a negative exponent. And we can go the other way. Okay, log base 4 of 1 equals, so this says 4 to some power equals 1. Well, what can I raise any power to equal 1? And that would be 0. And then the last one here says 7 to some power equals 7, and that would equal 1. So these answers generally, when you're simplifying or evaluating a logarithm, stay like under 5, like 5, 4, 3, a half, -2, 0, 1. Not very often do you get much larger numbers. Okay, so you have some properties here, and I'm going to let you guys write these down. But again, look at these properties, and they should make sense to you. Log base b of 1 equals 0. That means b to the 0 equals 1, right? This is my base. That's my exponent. Right here, when these two numbers are the same, that means the exponent's a 1. Again, when you rewrite these, it should make sense. Log base b to the y power equals b to the y. And then b raised to the log base b of x is equal to x because log base b of x equals log base b of x. So these are just simple properties that we have that deal with this. And there's another. We just did this problem. We know the answer is 3. But if I rewrote this as log base 2 of 2 to the 3rd power, right? Isn't 8 the same thing as 2 to the 3rd power? I could use this property right here when my base of the log and my base of the exponent are the same and just say, oh yeah, the answer to that is 3. Okay, same exact thing here. This could be written as log base 3 of 3 to the 1/2. When these two are the same, it just equals whatever the exponent is. And then this, you have 6 log base 6 of 11. Again, basically, I tell everyone, well, that log base 6 cancels out and it equals 11. Okay, so these properties kind of help us solve these and simplify them. I think the more you do these, the easier these become. I want to show you on this next slide, logarithms and exponentials are just inverses of each other. Look, if I have 2 to the x, right, 2 to the x, y equals 2 to the x, and I plug in -3, or -2, and -1, 0, here's all the x values. Well, with logarithms, I'm plugging in 1/8, 1/4, 1/2, 1, 2, 4, 8 to get the y values. See how they just switch? These values just switch when it comes to um, logarithms and inverses. These just switch. The y values and the x values just switch. So logs, really important, logs and exponentials or exponents are inverses of one another. Learn how to spell. Really important. Okay. So then we have this thing that's called the common logarithm. If you look at your calculator and you just see the button log, that means the base is automatically 10. Automatically 10. So again, when you see log with no number down there as the base, we had these problems up here where you can clearly see the base is 2, the base is 3, the base is 5. When we have these problems, there is no base. That means the base is 10. You can write base 10. So again, when you rewrite these, 10 to the 0 power equals 1. 10 to the first power equals 10. 10 to the y power equals 10 to the y. And then again, log base x equals log base x. So there's a few examples of these. I don't want you to get confused, but students always get confused. Like, there's no base. You're right. There is no base. What is the base? It's 10. So this, rewriting it, again, I always say rewrite it. Some people can do this in their heads. Some people need to rewrite it. There's my base of 10. Here's my exponent. It equals 100. What can I raise 10 to equal 100? That's 2. This one, 10 to some power equals 10 to the 1/5. Where'd I get the 1/5 from? Right? This is the fifth root, fifth degree, fifth root, the fifth root. Index goes in the denominator, exponent goes in the numerator. So what would x equal? 1/5. This one, 10 to some power equals 1/1000. How do I go from a whole number to a fraction? X has to equal a negative. In this case, it's -3 because -3 or 10 to the third power is 1,000, and we need it to flip. Then this one right here, 10 log base. Remember, this is a 10 right here. So these basically cancel, and it equals 6. Okay. And then we have the calculator problems. So these problems right here, these first 3, you're literally just going to go to your calculator. So I'm going to pull up and show you on Desmos, how to do this. If you go to Desmos, you notice there's no log button here. You have to click on this functions, and you have to click on miscellaneous, and it will take me to log. Now, if I'm dealing with log base 10, notice these 2 buttons are different, right? This is log base 10. This is log where you have to enter the base. So I enter log, and then the problem for this was 34.5, and I enter in whatever the rounded answer is that they want. You guys are still terrible at rounding. Okay, so again, you can do all of these problems. Want to make a note here. If you put in that last example, log base, so again, go to functions, put in log of -3. Notice how it says it's undefined. That's a really, really, really important fact right there. Okay, I can never have log of any base and a negative value here. This will always be undefined because what is this saying? It's saying 10 to some number equals a negative number, right? Well, that can never happen because if my exponent's negative, it just makes it a fraction. If my exponent's a fraction, it just makes it a radical. And if it's a whole number, obviously it's going to get bigger. So this will always be undefined. Okay. Then you have like some basic algebra equations here. Set them up, write them as an exponent. This says 10 to the third power equals x. Okay, well, what is 10 to the third power? It's 1,000. This says 2 to the fifth power equals x. That's 32. So these problems are really easy to solve once you realize just to rewrite them as exponents. Okay. So I want to look at the next thing, which is a natural logarithm. So you'll also see on your calculator the little button ln. I can't stress this enough. Just like we have the common logarithm where the base is 10. Here, the base is e. Okay, the base is e. So anytime you see ln, it's automatically base e. Same exact properties. Students always get confused with this because they're so used to seeing numbers. But look, there's a little e here. It's just not showing. So this says e to the 0 power equals 1. E to the first power equals e. E to the y power equals e to the y. So same exact type of properties. Want to look at a few examples of these. Okay, so again, don't get confused by this. Rewrite it. What does this say? E to the x power equals square root of e. Well, how can I rewrite the square root of e? E to the x equals e to the half. These have to be the same, right? So that's equal to a half. Here, e to the x power equals e to the fifth, x equals 5. And then right here, this e and this ln cancel, and the answer is just 4. Okay, so take a look at those. I want to make sure I look and show you the calculator. So again, if you see this, we're going to pull up Desmos, and we're going to go to the functions. You'll see the little ln button right here, and then just enter whatever it's asking you, 23.5, and it gives us our decimal answer. We would round it to whatever it tells me. Notice what happens if I put in ln of -5, undefined. Again, same reason as what I showed you before. You can't have something being raised to an exponent and it turn into a negative. Okay? So don't get confused with those. Just rewrite them and do those problems. And the last thing is graphing. Look, we've talked about this since 1.6. Okay, here's all the different characteristics of a natural log graph. It's the same thing if I were to say y equals log of 10. Okay, if I said y equals log of x, same exact types of transformations. Okay, so the domain is 0 to infinity. Why is it 0? Because there's a vertical asymptote. Okay, where do we find a vertical asymptote? Well, that's if I rewrote this as a times ln of x minus h plus k. H would be my horizontal shift. So that would be where my vertical asymptote is. That's where my domain would start. Okay, the range is negative infinity, positive infinity. It's continuous on from wherever the asymptote is, and it's increasing, going up from left to right. There's no symmetry, no bounded above or below, no local extreme, no horizontal asymptote, but it has a vertical asymptote at h. I'm going to change this a little bit and say x equals h using this. Okay, and the end behavior, as x goes to infinity, y is going to go to positive infinity, right? And behavior. And it's the same exact characteristics for this. This function would look like this: a log of x minus h plus k. This is my vertical asymptote. As we're doing, there's a couple of graphing problems that kind of ask you to simulate those. Again, what does this negative here do? If that value is negative, that's going to flip about the y-axis. I really want you guys to give this homework a shot. It's not super long if you can rewrite logarithms as exponents, but it's kind of a good just introduction to logarithms. And then we're going to do with more with logarithms next week leading up to break. Okay. Hope you guys have a great weekend. Again, sorry about not being here today, but got to take care of the kiddo. And like I said, have a great weekend. Go Browns.